Good morning. I'm Xiangzhou Yuan, research professor at Korean University. It's my great pleasure to give a talk. Today I will give my talk on valorizing waste PET plastic into porous carbon for CO2 capture, a route to the closed carbon loop. In the first part of my talk, I'm going to begin with a focus on plastic pollution, which is as dangerous as climate change. And then from engineering perspective, I will introduce how to effectively upcycle waste plastic, especially the plastic bottle, into excellent CO2 absorbent. Finally, the environmental impact of this process will be evaluated using life cycle assessment. I'm going to use 3 slides to introduce the plastic pollution. As well known, climate change is a very urgent and critical issue. Here, I also would like to say plastic pollution becomes as dangerous as climate change. Let's see some recent key publications. Our group published 2 letters in Science. One is titled as COVID-19's Unsustainable Waste Management, noted that protecting waste management chains will help achieve sustainable cities and communities as outlined in the UN SDG. The other one is to address the microplastics rules in antibiotic resistance. We highlighted that indirect effect of plastic pollution is still remain unclear. So the evaluation of both direct and indirect effect of plastic pollution to fully assess the environmental and public health risk should be urgently performed. In addition, Professor Adai published one letter titled as Accumulation of Plastic Waste During COVID-19 and made a conclusion that without a concerted effort to protect the environment during and after the pandemic, we are unlikely to meet the UN SDG. In the left chart, the plastic waste accounts for 12% of global waste. And in the right finger, we could see clear trend that plastic waste generation is far over the recycling rate in the following 3 decades. So the plastic waste issue will become a bigger issue. For more plastic issue, I do recommend to visit the Nature Forum on Plastics and Sustainability hosted by our university together with Nature Research. It covered comprehensive current research state, challenges, priority studies, and also potential policy on plastic and microplastic. So please visit this website and check the video. In this slide, I would like to give a bit more new findings. Professor Xing published one paper at Nature Nanotechnology and they verified that nanoplastic demonstrate distinct accumulation in plant root. And another one paper highlighted that the consumption of fish contaminated with microplastic may lead to a higher risk of exposure to bisphenol and adverse effect on human health over a lifetime of exposure. It suggests that plastic find their way to get into chains of both animals and plants, causing direct threat to human health. So extraordinary efforts to transform the global plastic economy are needed. Generally, we think those 2 environmental issues, plastic pollution, climate change, are urgent but stand alone. However, through upcycling plastic waste into porous carbon and then used for CO2 capture, those 2 issues could be mitigated simultaneously. For CO2 capture technology, adsorption has been considered as one promising pathway due to its low energy consumption for solvent regeneration, high feasibility for commercial application, and mild operating conditions. Among all different kinds of adsorbent, active carbon, here we also call it porous carbon, holds several advantages. Low price, especially the carbon precursors could be solid waste, and stable mechanical and chemical priorities, well-developed porous carbons. For the carbon precursors, here we are focusing on the PET plastic bottle because it is the most widely plastic production in our daily life. And also, could you imagine that human produce almost 20,000 plastic bottles every second? So in our study, we tried to convert plastic waste into CO2 adsorbent. So how to effectively convert waste PET plastic into CO2 sorbent? Generally, carbonization and activation are the crucial steps. After carbonization, we can obtain the biochar and hydrochar with poor structural properties such as the small surface area and total pore volume. For further improving the textural property, activation, including chemical and physical activation, is one efficient approach. After performing activation, the surface area could reach 2,000 or even 3,000 square meter per gram. So following this research conceptual, we conducted the experiment study. Based on the TG analysis data, the carbonization was set at 600 degree, and then activation was done using QH and NaOH respectively at 4 different operating temperature. Finally, among those 8 prepared samples, the PTKOH 700, it means activated by QH at 700 degree, presented the best CO2 adsorption performance. I will show you more detailed information. From the same image of PTQH700, the well-developed micro-pore structure could be seen clearly. It means the QH activating agent is thought to progressively react on the surface of carbon materials and then go through in an inner part of carbon materials. And at the top right corner, this table lists the texture property of all prepared samples such as BT surface area, total pore volume, macro volume. Left bottom figures show the CO2 adsorption data in using different prepared samples. We can find that PTQH700 showed the highest CO2 adsorption capacity. It is worth to be noted that CO2 adsorption capacity is not directly related with surface area or total pore volume. So further investigation was performed for figure out the reason. We listed the different pore volume limited by narrow pore less than 0.7, 0.8, 0.9 nanometers respectively, as we can see in this table. And then we figured out that a very good linear relationship was obtained between the CO2 uptake and cumulative pore volume by 0.8 nanometer. It mainly because the kinetic diameter of CO2 molecule is 0.33 nanometer. The pore size at least two times higher than CO2 kinetic diameter is the most effective for the CO2 adsorption. Considering the environmental impact of this process, we further did a life cycle assessment using the best CO2 adsorbent. The basic use of PET plastic bottle was well fitted with the linear model like make, take, dispose. In this study, we recycled the waste plastic bottle into active carbon and then further to be used for the CO2 capture as mentioned in previous slide. Finally, the scrapped CO2 adsorbent can be used for the soil amendment during the landfilling disposal. As we can see in the bottom figure, we consider the 4 phases in this whole system boundary, such as BT bottle production and collection, activity carbon production, CO2 capture, and the activity carbon disposal. The environmental impact was categorized into 11 environmental midpoint indicators. The impact of GWP and W show higher magnitude in weighted impact potential. Additionally, there is a significant energy demand in CO2 capture and active carbon preparation process. So the impact of GWP, W, and PD are selected for further analysis. As shown in the left up finger, GWP reached minus 1,805 kilogram CO2 per kilogram active carbon, suggesting that the negative CO2 emission could be achieved and the absorbed CO2 capacity is much higher than CO2 emission from the PT production process. But the PD reached over 5,000 MJ per kilogram because 8% of total PD was consumed by adsorbent regeneration process, and also the W impact cannot be ignored. We further performed the CO2 capacity duty study by increasing up to 3.73 MJ per kilogram from 1.5. The impact of PD doubled, reaching 11,034 MJ kilogram per kilogram active carbon, and the GWP increased by 20%, but still maintained negative. On the contrast, W also almost unaffected by CO2 capture duty. Only mineral growth was observed. In addition to energy duty, the energy source for CO2 capture is also an important factor affecting environmental impact. So 5 more heat sources were further analysis, including heat from solar collector system, municipal waste incineration, biogas heat, and power cogeneration system, wood chips, and hardcore industry furnace. As we can see, biogas and wood chips demonstrate a significant PT reduction because primary energy from fossil fuel was substituted. Regarding to GWP, the substitution scenario of solar, biogas, and wood chips showed a good improvement in GWP mitigation effect. It is further noted that solar energy was accounted for as a kind of primary energy in the characterization calculation process in software. However, in fact, the solar energy is indeed renewable energy. So the high PD value of solar case cannot indicate that the scenario is not favorable in terms of fossil fuel depletion. In this slide, the bottom-to-bottom scenario, B2B, was considered to understand how this modeling choice affected the result, which is given in left up finger. And in left bottom finger demonstrated the result of PED, GWPW, when changing the share of recycled PET flake used for the boat production. We could figure out that the overall environmental impact of this entire system showed a reduction trend. Specifically, the value of W decreased significantly by over 25% when the share of recycled PET flakes reached 100%. Similarly, the PD also showed a notable decrease trend by nearly 8% with 100 share of recycled PET flakes. Regarding GWP, slight decreasing tendency of around 1.5% was observed because the PET manufacture was not the major contributor to greenhouse gas emission. And finally, we made a conclusion that waste PET derived porous carbon for CO2 capture could achieve the closed carbon loop. And this research was published at Green Chem and also highlighted in the back cover. Take-home message. Here I listed the UN Sustainable Development Goals related to plastic pollution from 4 aspects: production of plastic, impact from plastic pollution, valorization of plastic waste, global effort, collaboration in resolving plastic pollution. It suggests that we need to pay more attention on how to effectively reduce plastic waste, how to efficiently upcycling plastic waste into value-added products. The concerted effort should be performed urgently, otherwise our humans' living environment will be surrounded by plastic waste, and also the ecosystem will be destroyed by plastics. Welcome to join us. We will host this nature conference in October of 2021. The topic is waste management and valorization for sustainable future. And three nature editors from Nature Sustainability, Nature Electronics, and Nature Nanotechnology will be the co-organizer together with our university. We sincerely invite all of you to join this big event. Hope to see all of you by face-to-face next year. For more information, please check the conference website. Thanks for your kind attention. If you have any question, comments, please feel free to contact me using this email address, and please visit our group website for checking our research and publications. Thank you.